Hi, my name is Marwane Hariat. I will present rebalancing gradient to improve self-supervised co-training of depths, odometry, and optical flow predictions. So the goal is to co-train those networks in a self-supervised learning settings and to benefit from their specific insights to enhance learning process quality. So the main challenge is to locate moving pixels in an image in order to remove them from the computation of the loss and better train the depths plus odometry networks. The self-supervised training procedure is based on the warping process where you try to reconstruct a target view at time t from a source view at time s, and the quality of the reconstruction is assessed by an operator that gives the supervision signals. There are two ways to warp an image. Either you use the depth plus camera network, or you use the optical flow. The issue with the first method is that it's no longer valid in moving regions. So it gives overestimated loss values that disrupt the backpropagating process. So we have to account for moving objects, and we can either add a residual correction to do so, or remove pixels from the loss. This is the second option that we will follow. So let us define the random variable delta based on the operator that assess the reconstruction of an image. When delta is positive, it means that the flow is better or reconstructing the image. And when delta is negative, it means that the depth with odometry is better. Statistical analysis of delta gives us the following distribution. Please notice that the flow is naturally better because it's less constrained, so it can better reconstruct an image. And that's why the distribution is slightly biased toward positive values. GenNet is a very recent and performing methods that is based on the random variable delta. So it's changed the operator that assess the reconstruction of the image as follows. And the underlying assumption is that positive values correspond to moving region and the flow should only be trained on them, whereas negative values correspond to rigid pixels and the depth with odometry should only be trained on them. This assumption is wrong because as the statistical analysis on Kitty and the following hot color maps shows us, rigid pixels are actually localized around the mean value, whereas the left part of the tails correspond to moving objects for which the optical flow faces smoothing issues. That's why we propose a quantile-based split of the probability density function, where we train the depth-based odometry networks on this very tight neighborhood of the mean value in order to train them on most of the rigid pixels. And we train the flow on all of the pixels with a specific focus on the tails. This gives us the following results. We can see that we are on pair or better than the most recent and performing methods, be it in depth, odometry, or flow. And here you can see the qualitative results where our methods clearly shows better depth map quality. Thank you very much.